thank you. Thank you all for coming and welcome here to OGP UK. So I'm Colby Finn. I'm responsible for strategic marketing for OGP. So this is planning future products, doing business development, seeing what our customers want, seeing what they need. I've been at the company for 16 years now. I started out as an applications engineer, then I moved to research and development, and then I finally moved to marketing. So it's an interesting background for a marketing person, but it's been very useful in developing the next generation technology. So my actual school education is in optical engineering, so we're going to get a little bit technical this morning, so I apologize if it's a little dry. So I'm going to give a little history, a little background on OGP, who we are, what we're doing, and then talk about our technology. What are the challenges we face, and where we're going in the future with our video multi-sensor technology. So get started. I have about 20 minutes of presentation material, and there should be time for questions at the end. So OGP is headquartered in Rochester, New York. There's a picture of our facility. We do all the designing and manufacturing in New York, the United States. We are the global market share leader in video multi-sensor systems with our smart scopes. So we have over 70,000 smart scopes installed worldwide. We were founded in 1945, so it's a 78-year-old company. It's a family-owned, third generation now. It's a very nice environment to work in. And so we make general purpose measurement equipment, meaning we don't target a specific type of manufacturing or a specific industry. Our machines can solve medical applications, aerospace, electronics, plastics, all different types of manufacturing. Due to the multi-sensor, it's very, very flexible. So we have about 500 employees worldwide, and we have tech centers like this one in about 10 different countries. But in addition to that, we have over 80 local channel partners that represent us and sell our equipment. So a little known fact, Rochester, New York is actually the worldwide center for optics and photonics research. So we do more research than anywhere else in the world. We grant more patents, have more students that study optics. So this is a great place to have an optical company. We can collaborate with local companies, universities, and it's a great space to really learn about optics. So here is just a map of our offices. Again, we have a lot of locations in the United States, in Europe, and in Asia. So what we do as a company is transform optical metrology, meaning find new and innovative ways to measure things non-contact. So when we first started in the business, we sold optical comparators, where every measurement was taken with your eye. And now, with our smart scopes, you pretty much can't do anything without software. So we've transformed from a hardware-only company to more of a hardware and software company to really get you the best non-contact measurement. What's unique about OGP is we design and manufacture just about everything that's critical for non-contact measurement. Meaning we do our own transports, we do our own optical sensors and our optical systems and lighting. We do our own non-contact sensors, lasers, and triangulation sensors. And we do our own image processing software. So again, it's a combination of your hardware and software that really allows you to solve those tough applications. We do it all ourselves. This slide is just showing a brief overview of our product offering. Across the top, you'll see our smart scopes. We have a very, very large variety of video multi-sensor systems available. These are different magnifications, different working distance, different ways to solve the customer's problems. Our flagship software is called Zone 3. It's our CAD-based metrology software. I'll be talking about that later this morning. But in addition to the smart scopes, we also have 3D scanning laser systems. You'll be hearing about them from Mr. Dave O'Connor this afternoon. We have multi-sensor CMMs for larger part measurements. We still sell a lot of optical comparators. We have more than probably 500 a year still. So some people like that technology. And lately we've been getting into large field of view systems. A little more on that. So there's 3 topics I'm going to cover today related to OGP technology. Video measurement, which you see on your smart scopes all around here, non-contact sensors like lasers, and automation through CAD. So first we'll talk about video measurement. So when I say video measurement, I mean we're using an image of the part to measure it. So we're not measuring the actual part, we're measuring an image of the part. So you need very high quality optics to replicate that part, to have that high fidelity image. And you need high quality software to turn those pixels in your image into real life measurements, into microns or millimeters. So why choose video measurement? The number 1 reason is throughput. You can measure things faster than you can with say, a CMM or other technologies. And it's just not it's not only the measurement process itself, not only the runtime, but it's easier to set up the program when you can actually see what you're doing. You can align the part, you can find a feature first with the video sensor and then measure it with a probe. So there's a lot of time savings involved with video measurement, and that's why customers choose video measurement. In addition, it's obviously not contact, so if you have a fragile part that cannot touch, measure it with video. And you can get very, very high resolution, precision, and accuracy. Especially if you're doing a measurement in one field of view where you're not moving your transport, you can easily get sub-micron accuracy on a video system. So we're going to go over a couple of terms before we get into the technology. When I say field of view, I'm referring to how much of the part you can see in one camera image at one position. So most of our smart scopes, the maximum field of view you can get is around 10 to 20 millimeters. And this is what I would call a traditional field of view. When I say large field of view system, I'm referring to something that has about 100 millimeters of field of view, where you can see that much of the part at once. So if you can see more of the part, you can measure faster, because you can fit more features in one camera snapshot and measure them all at once. But there's always trade-offs. So when you get a larger field of view, you're giving up measurement resolution. So you can't necessarily measure features as small as you could on a smaller field of view or get that accuracy that you need. So it's always a trade-off. And how do you change field of view? That's with optical magnification. So when I say optical magnification, I'm talking about the ratio of your part in real life to the image that's made on the camera sensor that is then measured. So again, the higher mag, the smaller the field of view, but typically the more accuracy you can get. The next concept is depth of field. Sometimes this is referred to as depth of focus, but technically it's depth of field. It's how far in the Z direction your image remains in focus. So you don't always have to be in the perfect focal plane to measure. There's usually a region you can move up and down and still get high quality measurements. So some systems with large field of views have very large depth of field, meaning like 100 millimeters. So you can see the part in your hand. You don't have to move Z to remeasure, so it gives you a lot of throughput advantage if you're not refocusing all the time. But again, there's always drawbacks. If you have a large depth of field, you can't get that autofocus accuracy to take Z measurements. So if you get a large depth of field, you can measure faster in X, Y, but your precision in the Z direction goes way down. So again, it's always a trade-off of optical technology. So now we're going to talk about some common errors you see in video systems that may not be obvious to the user. So the first is distortion, optical distortion. And distortion is a change in magnification throughout the field of view. So what this means practically to a user, you'll get a different measurement result if you measure in the center versus in the corner or in the bottom. And so there's really no point in having a larger field of view if you always have to measure in the center. So we always want distortion-free optics or distortion-corrected optics so you can actually use the entire field of view and not be forced to use the center. The second error is called lack of telecentricity. You'll hear us talk about our telecentric optical systems a lot around here. And if your system is not telecentric, it changes magnification as you move in Z away from best focus. So we have that depth of field, that range in Z where you can measure and you can still see the part. But if you're not telecentric, your XY measurement results will actually change depending on how far away you are from best focus. So what you're seeing on the screen is actually from a different manufacturer's optical system at low zoom, where the circle, you can literally by eye see how it's changing size. And if you can see it by eye, it's very, very bad. I mean, this would be probably 300 microns of error. So the tricky thing is a lot of optical systems don't have telecentricity, but it's not obvious by eye. So you get like a 5 to 10 micron error that if you didn't know how to test for it, you wouldn't see it. You just get your results. Another way to see that your system's not telecentric, if you have that large depth of field and you move a hole over to the side of the field of view, you actually start seeing inside. You see the walls of the hole. So if you see something like that image on the left here, you know that your system's not telecentric. If you put it in the middle, you see straight down the hole. You put it to the side, you start seeing the walls. That's another, we should make you question things. It doesn't necessarily mean you can't measure that magnification. You just have to make sure you're in good focus. You want the best results. So a little bit about OGP's technology. We say we have a metrology grade field of view. So some other manufacturers say their low mag, their low zoom is only for navigating around the part or an overview camera for finding features, but ours is actually for measurement. So you always get better accuracy if you go up to higher mag, but our low zoom is very, very good. It's low distortion, and when we say an optical system is telecentric, we mean all of the optical zoom positions are telecentric. Where some people will say it's telecentric, but that's only at high zoom or only at a certain position. So that's a little bit about our hardware. And again, we do our own software too. And to take that image of your part and turn it into real life measurements, you have to do what's called edge detection. You analyze the pixels on the camera for contrast to find what's the real edge of the part. So what I think we as a company have done really well is taking a lot of the smarts out of the user and putting it into the software to pick that correct edge. So yes, we have a lot of settings to help you tweak and get more part repeatability. But one of our strongest strengths as a company is our edge detection. It allows you to get repeatable measurements, even if there's part variation from lot to lot. And a lot of people don't realize you can actually measure in the Z direction with the optics. It may not be as quick as, say, a laser or as accurate, but our systems are very, very, relatively speaking, accurate in the Z direction. Typically better in XY, but you still get very good measurement in Z with the autofocus tool. And if you see in the bottom corner, you can actually do 3D measurements with our video systems, where you take a whole chunk of the part and get a 3D scan over a little area that you fit inside the field of view. So in summary, what we have today is a very high throughput measurement system. So we have a large field of views that you can actually use to take advantage of the speed improvements. We have a very flexible product offering. Lots of different lenses and zoom systems to give you different magnifications, different working distances if you need to be farther inside or away from your part. We have very robust and repeatable edge measurement, and we have accurate Z measurement. So a little bit about where we're going. So again, since we do our own lenses, our own lighting, our own compensation algorithms, and our own image processing, this gives us the advantage to really create unique technology in the marketplace. So an example of where we're going is actually the SmartScope SP systems you'll see around here. So like I said, everything in optical design is a trade-off, but what we're trying to do is minimize those trade-offs. So we're trying to increase the field of view while maintaining the accuracy and resolution. So the SmartScope SP actually uses the same zoom system as our SmartScope Zip product line, but it has twice the field of view, but the same resolution. meaning you can measure the same smallest feature even though you have twice the field of view. And how is that possible? It's through unique optical designs, unique software, and higher resolution cameras. So a lot of people think you can just take a megapixel camera and improve your measurement resolution on one of our systems. That's not the case. You have to redesign the lens, redesign the lighting, redesign the software. So it's not as simple as just one component. It's really all of them combined that allow you to minimize the trade-offs. So we have a new system. It's not here, but it's called the SmartScope E7. It's one of our entry-level systems. And because of our software and hardware, it doesn't actually use a zoom lens. So you have effectively a 5x optical zoom range, but with no moving parts. So again, you don't have the loss of accuracy, you don't have a zoom barrel wearing out after many uses. So this is where we're going with all of our products, trying to make them more reliable, have larger field of views, but not compromise on your measurement accuracy. So you'll be seeing more products from us with better features. Now a little bit about our non-contact sensors. So on our CNC product lines and our ZIP product lines, we have what we call the traditional TTL laser or the off-axis DRS laser. And both of these are very general purpose lasers for accurate surface or Z measurement. So they're based on a technology known as triangulation. And with triangulation lasers, the steeper your triangulation angle, the more accurate the technology is. But what that means is you lose working distance. If you want higher accuracy, you have to get very, very close to the part. And also because of triangulation, you're sometimes hitting the walls of the part, and you can't quite get the feature you want or get to the bottom because it's all based on angles. And again, it's very good general purpose laser, but there's some trade-offs involved. We also offer the white light sensor. Technically, it's known as a chromatic confocal sensor. And in marketing, we call it a rainbow probe. And this is very great for glass or shiny surfaces. So this technology is sub-micron resolution. It's very high accurate, but it has some drawbacks. It also has a tiny working distance to get that accuracy. And it's not as great at a diffuse surface. So when I say diffuse, I mean a surface that scatters light. So only very shiny surfaces like a mirror or glass will just be where you get the best performance. You start moving to more machined, real-life parts, you typically don't get the best performance. The other technology we use for Z measurement is interferometry. So this is what's called our Telestar Plus laser. It's available on our SP systems and our Vantage line. So this is not based on triangulation. So it's through the lens, but there's no angle to worry about. So you're never interfering with the walls. It can handle both shiny, both specular surfaces and diffuse surfaces and not compromise on accuracy. And your accuracy is not dependent on the working distance. So I almost want to say there's no drawbacks to interferometry, meaning our Telestar Plus, but it's a little more complicated to use and it costs more to manufacture, so it's a little more expensive, but that's kind of where the trade-offs get minimized. So where are we going next? With non-contact sensors, we're focusing on increasing the accuracy of 3D non-contact technologies. So all the lasers I just talked about are point sensors. So you can draw a line on your part, but you don't get they're not 3D scanners. You don't get a lot of data very quickly. You get a lot of data compared to the video system, but not compared to a 3D scanner. So we've been working on improving the accuracy of our 3D laser scanners, and Dave will tell you more about them this afternoon. But incorporating them into our software and into our systems is on our roadmap of, again, to make measurement faster and more accurate for you. So not only are we focused on 3D hardware, we're also focused on 3D data processing, making the software side easier. So like I said, one of our strengths as a company is our edge detection, our feature finder tools that allow a user to find the right edge for video measurement. So we've been doing the same thing for 3D measurement, specifically for GD&T. So when you're doing GD&T, every single point matters. So your result is whatever is your worst case away from your nominal. So when you take 3D data or a 3D scan on your part, you get a lot of noise and you have to clean it up. And again, this takes a lot of experience, a lot of user interaction. So we've been trying to add intelligence to our software so that you can take a 3D data cloud and actually do GD&T on it where every point matters. So I'm going to show you a quick video here. This one does not have sound, so I'll talk over it. Just show an example. So again, this is a way to get fast 3D and GD&T results without the user needing that much training. So you do need a CAD model to do this. So you'd import your CAD model with the tolerances added already, or you can add them. This is our Smart Profile software, by the way, if you want to learn more. Then I'm going to import my measured points that were actually taken on Shape Forever by one of our laser scanners. And you'll see the green data is the scan data overlaid onto the CAD. And although there's a lot of data, it's not all valid. There's some outliers, there's some noise that needs to be removed. So now we're going to run what's called the CMM-like sampler. So this is that intelligence I was talking about. It's going to take that point cloud and process it automatically so it looks like it was probed with the CMM, but very densely. And this will both minimize the uncertainty and increase the accuracy, so your point cloud is ready to do GD&T. I don't know if you can see it, you probably can't see it very well on your screen, but there's a little green array of dots. That is the after the CMM sampler data set. So now that I've cleaned up my data, I can now do GD&T with confidence that the flyers aren't influencing my results and changing my measurements. So we see more and more customers adding 3D scanning into their metrology realm. It used to only be used for reverse engineering or for more R&D efforts, but it's becoming more and more of a pass-fail tool that can be trusted for high accuracy metrology and even doing GD&T. So the last technology topic we're going to talk about is automation using a CAD model. So again, later I'll talk about Zone 3. We'll focus more on how to program from CAD. So we won't go too far into the details right now. Here's an image of our Zone 3 software. So most of our customers are using Zone 3 to easily navigate around the part, easily generate finders to do their measurements. But we actually have automatic programming in Zone 3. Meaning you can import the CAD model and the tolerances and have it create the routine for you. I'll show a little video of this and then I'll explain where we're going. We don't have a lot of customers using this quite yet, and there's a couple of reasons why. So what I'm going to import into Zone 3 is what's called a QIF file. It's a quality information framework. It's just an international standard for containing a CAD model and its tolerances. So this is reason number one why a lot of customers aren't doing this. Their designers don't produce QIF files that contain the CAD and the tolerances in there. So Zone 3 said if I found features, I found tolerances in my file, would you like me to create measurement steps? So I said yes, and now I can choose how to measure the features. So in this QIF format, you can actually store how you want the feature measured, meaning a measurement strategy, what we call like a step template in Zone 3, like what tool you're using, so you're using a probe, what point density, what scan strategy you want. They can all be stored in the CAD model and brought automatically into Zone 3. And if it's not there, you can just create it as you typically would. So once you do that, you can say, generate my program, and the software is smart enough to know if you have a profile call out related to, say, 2 datums, it will know to measure the datums features also. So it'll actually call it reverse programming. It takes your final result you want and backtracks and adds the features you need to do. So the video is a little ahead of me, but now it's measuring the part again with the user did not set any binders themselves, it did it all automatically. So this is a direction we've been doing a lot of research and a lot of advancing in. But like I said, we don't have a ton of customers using it yet. And the main reason is that the PMI, the tolerances are all 3D tolerances. So it's really only, this automatic programming is only valid for probing. So most of our customers use a lot of optics, where instead of measuring the cylinder, you might measure just a circle on top for a hole. And that really doesn't work well yet with the QIF standard and how it's implemented. But we see this improving in the future. And you'll see how Zone 3 in general is very easy to program from CAD, and I'll show you that later this afternoon. So it's not a deal breaker, but eventually we see this world where machines can program themselves. That's the vision. We'll see if that ever comes true. All right. And the last thing we're doing is trying to get closer to the manufacturing process. Okay. So also focused on GD&T. So GD&T will save a company a lot of money, but only if the entire organization is doing it properly. Meaning the design engineers are following the standards, the quality engineers are measuring and evaluating the tolerances correctly, and then the manufacturing engineers and machinists know what to do if the GD&T fails. So we found in many companies, if you give them quality gives manufacturing a failing profile tolerance, they say, I don't know what to do with this. I want to know process control. I want to know how to offset my tool. I don't want your profile tolerance results. So we have a software package called Evolve Manufacturing that helps bridge the gap between your GD&T, your functional coordinate system, and the machinist coordinate system of how they make the part. So I'm going to show a video on this because it's a little confusing. But this is again where we're headed with trying to get closer to the manufacturing process. So this is a project already loaded in Evolve that has the points and the tolerances already evaluated, or about to evaluate it. And we'll see that a couple things fail, I believe. So I see one of my runout callouts failed. And see, I didn't really know what this meant. Evolve has the GD&T standards embedded inside it, called an explanatory system to explain to the user what this column even means and why it failed. So now that I know what total runout is, I still don't know how to fix it. This is what the software is going to help us with. So in order to adjust my manufacturing process, I need to have the operations loaded into the software, meaning which features are manufactured together, which features are allowed to translate or rotate as a group. So I can either import that directly from a CAM program or in the software set up my operations. So here I believe I imported some of them, but I'm going to manually set up a new operation, saying these cylinders were manufactured together and therefore will shift as a group. So once I have my manufacturing coordinate system, I can view my data points in the different manufacturing setups as opposed to my GD&T coordinate systems. What I'm going to show you now is how to optimize the results. So what we have is called what-if simulation. So the operator can type in, what if I move this operation, translate this tool or my data fixture setup by 100 microns? Will that make my GD&T pass? Or can I put a tool offset it? So that's the first level of simulation. What I'm doing now is saying, I have no idea what to do. Software, you figure it out on your own. So I selected which operations are allowed to be flexible and said, hey, recommend how to fix the part, essentially. So that's what it's doing right now. It's chunking through all the possible operations that could change and optimizing the GD&T. So what you see on the screen is what it suggests. So here, I think we'll highlight it. It's suggesting to get that run out to pass, I actually shift operation 1, which is datum C, over, I can't see it, it's too small on my screen, but over in X and Y. And then in the middle, in the model window, they'll show you the before and after results. So the left is the as found results, and the right is if you made this manufacturing adjustment, hypothetically, what would the passing results be? So the whole point here is to get future parts to pass. And again, this is available in our Evolve manufacturing product today, where we're migrating this functionality into Zone 3. So we're trying to get all of it into our one master package. You can do as many coordinate systems as you want. So originally it's best fit to do the filtering, but then to evaluate you do, it doesn't have to be fully constrained or whatever you want. So it's very flexible. The question was, if when you put the 3D data into the CAD model, how is it fit? Is it best fit, or do you align to datum surfaces? And it's whatever the user wants to do.
Anyone questions for Colby? She will be back later, so if there are, and everyone's been shy at the minute, we can ask later on.
Sure.
Yes. Okay. Thank you.
Thank you.
Colby.